tucked your way into my heart. Oh, you look at me in ways I never loved. With you I know that this is all, so I don't need to take it slow. If you want me, then I believe that there's a simple remedy. We don't need no miracle, I think we've seen it all, just make the call. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. Don't need a miracle. Need a Oh, you open up a world behind the stars. Oh, you make me see the things I never saw. With you I know that this is all, so we don't need to take it slow. If you want me, then I believe that there's a simple remedy. We don't need no miracle, I think we've seen it all, just make the call. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. We don't need a
Those medical pills all push me over. I kill my fill 3 times a day. These ethanol fumes won't make me sober. One flame to take the pain away. I caught you lighting matches in the back room. Haters look mad when they pass you. Let's talk about round when it's past 2. Reach a glass to know you don't gotta fight alone. You don't gotta fight alone. Don't be so personal. Take me out of the Everyone's seen death in their dreams, but we still wake up and go to sleep. Everyone's Someone seen death in their dreams, but we still wake up from our sleep. I'll be home soon. You don't gotta fight alone. You don't gotta fight alone.
There's not a single day that passes without you on my mind. Not even 1 minute can end up before you come around. I yearn for the days when I see your face here before me. I long for the times you held me in your arms. Whoa. How I wish that you were here to give me everything I want. But I know that life's unfair and we can't always have it all. Whoa, whoa, I wish that you were here. Whoa, whoa, I wish that you were here. 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 There's not a single day that passes, not even 1 minute can end up. I yearn for the days when I see your face here before me. I long for the times you held me in your arms. Whoa. How I wish that you were here to give me everything I want. But I know that life's unfair and we can't always have it all. Whoa, whoa, I wish that you were here. Whoa, whoa, I wish that you were here. 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 I
Yeah. Unknown Brain, Marvin Divine, and we back. I'm saying bye to all the lies and all the times you cried, saying that I wasn't right, yet I was right by your side. You manipulator, playing games, your friends commentators, and I don't know what you say about our private conversations, but it's got them hating. Thanks to all the rumors you be claiming. It's cool, I'm done with you, so they can throw you a celebration. You gon' hate it when you see me with somebody living better. I'm trying to tell you that me just doing me gon' have you jealous.
I know that I gotta stay away from all your games. Yeah, I know that I found somebody else to love me one day. Yeah, you'll realize the grass ain't greener on the other side. No, you did me dirty for the last time, so now I gotta say goodbye. So now I gotta say
Yeah, my life is lovely now, I'm focused on me. You said you were about to die, I guess the car is on E. But see, I ain't even tripping, cause I just chose to believe that somebody gon' come around and give me just what I need. I don't wanna see you frowning, see you looking down and out, coming to me crying, saying you miss having me around. Gave you chances and you blew it, you so easily influenced. All the times you told me beat it, now you gotta face the music. I'm saying
I know that I gotta stay away from all your games. Yeah, I know that I found somebody else to love me one day. Yeah, you'll realize the grass ain't greener on the other empty hearts and neon lights. They're playing with my mind. Gotta get out of here tonight. Oh, I wanna run off and fly. And I'll tell myself it's fine to be alone, just to find somewhere that finally feels like home. Oh, oh, oh. I hate all this overthinking. Oh, 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 oh. The more I swim, the more I'm sinking. Take me to a world of silver. No more heartbreaks, tears, painkillers. Take me somewhere unfamiliar. Bring me back to where we started out. Get me out of now. To where we started out. Get me out of now. To where we started out. La 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 la, oh, oh. Get me out of broken hearts and starting fights, turning truth to lies. Gotta get up, stop wasting time. Yeah, I wanna run off and fly. And I'll tell myself it's fine to be alone, just to find somewhere that finally feels like home. Oh, oh, oh. I hate all this overthinking. Oh, 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 oh. The more I swim, the more I'm sinking. Take me to a world of silver. No more heartbreaks, tears, painkillers. Take me somewhere unfamiliar. Bring me back to where we started out. Get me out of now. To where we started out. Get me out of now. To where we started out. Oh no. Oh
Ten seconds. Stabilizing. Hibernation activated.
All the things we do for dreams. All of the things I do for me. I know the world is saying nobody wants to do it for Jesus.
skin, you can see it beat, intoxicating your energy. First time in so long you felt the heat, evaporating your bindings. Move like the sunlight, darkness can't hold you here. Bold and bright, push through the atmosphere. This is your dawn, this is your break. Move like the, move like the, move like the sunlight, darkness can't hold you here. Bold and
transcribing it wrong, something weird like that. Also, when Doug gets going in his, we're going to be doing some old law stuff, and I'll be passing out scratch paper and pencils. You'll see the question up on the screen, and then you'll figure it out. Most of the stuff you can do it in your head, though. It's really simple, that simple of a math. But that's the only oddity, and then after he gets done with his 2 sections, and I'll do the last 2 sections, and we're going. Doug, it's yours.
Okay. Level 1 technician. Electricity. Fundamentals of electricity. Radios are powered by electricity, and radio signals form a form of electrical energy. A basic understanding of how we control electricity allows you to better install and operate your radio.
Doug, I'm going to pause you for just a second. Having a bit of a technical difficulty on my end, so I apologize. The stream's not coming through on my side for this. There we go. I think we're good now. Sorry about that.
Okay. Electrical charge can be positive or negative. Opposites attract each other. Positive and negative, they all attract each other. Electrical current is the flow of electrons. Electrons are negatively charged atomic particles, usually surrounding an atom's positively charged nucleus of protons positive and neurons neutral, no charge. Electrons move in response to electromotive force, which is voltage, and can move independently of atoms. Basic electrical concepts. Current is the movement of electrons measured in amperes by an ammeter and represented by I in formulas. I in formulas is Ohm's law, so I is always current. Voltage is the amount of electromotive force, EMF, also called electrical potential, measured in volts, V by ohm, and represented by E or V in formulas. So you get the Ohm's law, the pie chart, you're going to see E is voltage. Resistance, the opposition to the movement of electrons, measured in ohms, omega, by an ohm meter and represented by R in formula. So when you get an Ohm's law, R is resistance. Am I going too fast for anybody? Resistance is like friction and turns electrical energy into heat when current flows. Like you see in a light bulb, the old incandescent bulbs, all that resistance turned to heat. That's why those bulbs got so hot. It's that current flow through there. Like your electric ranges, those elements, that's current flow. That's, see those old things get red hot. That's the current flowing through them. That's resistance. That's what makes them get hot. Conductors permit current flow, low resistance, and insulators block current flow, which is high resistance. Resistors limit current flow, but you get the big things like glass, that pretty much restricts it. Glass is not a good conductor. I'll highlight all this here. Basic electrical concepts. The flow of water through a pipe is a good analogy to understand the three characteristics of electricity and how they're related. So here you got water. Look at it this way. You got your kitchen sink. Okay, you've got a water line coming up to it. That is voltage, water pressure. Okay, when you turn your knob, that's resistance. So when you turn that knob counterclock, you know, your flow chart, your amount of flow coming out, that's the water, that's the current coming through. So that knob you're turning is resistance. You still got the same amount of pressure, but it's the flow of the water coming through. That's your current coming through. So all that big knob does is it's resistance. It's a variable resistor. That's really all it is. So if you look at all this here, shows you all this in here. Voltage from a source of electric energy causes current to flow. That's what pushes your current through the wires is electromotive force. Resistance is a material's opposition to the flow of current. Voltage, current, and resistance affect each other. For example, higher voltage, bigger push causes more current flow. So think of it like water pressure. You don't have enough water pressure, you're not going to get much coming out of your faucet because you don't have the pushing through it. Two kinds of current. Current that flows only one direction is called direct current. Like you see up here. Batteries are a common source of DC. All batteries are DC. 1.5 volts, 9 volts, 6 volts, 12 volts. That's all direct current. It only flows in one direction. Current that flows in one direction and the opposite is called alternating current, like you see here, like a sine wave. Goes up, peaks, down, back and forth like that. That's called a sine wave. Household current is AC, like you got in here. It's all 60 cycle AC. 120 volts, 230 volts, it's all alternating current. AC current reverses direction on a regular basis, like you see here. Negative, like this. That's going, if you put that in a oscilloscope, you see that sine wave 60 times a second. So this light is actually going off and on 60 times a second, but we can't differentiate that speed. So that's why you don't see that going off and on. Now if it was like 20 cycles per second, off and on, off and on, and off and on, but it's kept at a regular speed, so you don't see that variance in it. Each process of reversing is called a cycle, like you see here. The number of cycles per second is frequency measured in hertz. So you got 60 hertz. It's just like you only got 3 hertz in that graph. 1 hertz equals 1 cycle per second. So I got 1 cycle here. An electric road map. For current to flow, there must be a path from one side of the energy source to another side of the source. This path is called a circuit. There must be a pipe, conductive path through the water flows through the flow, whichever the water current can flow. So there's a conductive path in there. There are 2 types of electric circuits, series and parallel. Series circuits. It's like you see here, it goes from one end to the other, back and forth into here. So if one of these was to break, it's going to break your path. Let's say I got 12 volts here. I got 3 4-volt lamps. If one of those lamps was to fail, you're breaking your circuit. Now parallel, you see here you got a constant voltage here all the way across. So if one of those was to open up, you still got a complete circuit. Because you got, if positive goes through here like this, and if negative goes through here like, you don't have that series string on it. So if one of those lamps was to open up, you still got a complete circuit. Electric current is measured in which of the following units? Amperes. Current is always measured in amperes. What is the name of flow of currents in electrical circuit? That's voltage. I'm sorry. One direction. That's direct current. It only flows in one direction. And that's your, in the book, that shows you, that's your section of T5A05, that's in the book. That's one of the study questions right there. Electrical term for electromotive force that causes current flow. Voltage. Remember, that's electrical pressure. It's push. Like pneumatic pressure, air pressure, hydraulic, it's all push. What is a good conductor, electrical conductor? Copper. It's a very good conductor. What is a good electrical insulator? Glass. You're not going to push much current through glass. It's too restrictive. What is the name for a current that reverses direction on a regular basis? Alternating current. Like I showed you in that sine wave, it's up and down, up and down. So that's you want to remember that. Basic unit of electromotive force, that's your question down here. T5A11. That's the volt. Electromotive force is the volt. What describes the number of times per second that alternating current makes a complete cycle? Frequency. Number of times that sine wave oscillates between negative and positive. So remember the word frequency. Which instrument would you use to measure electric potential, electromotive force? That is question. You got to remember that. A voltmeter. Oops. Voltmeter to a circuit, okay. In parallel with the circuit. See, I might have gone. Okay, voltmeter for that one. Which is the correct way to connect the voltmeter to a circuit? Question T7DO2, you got to remember that one. In parallel with the circuit. Am I going too fast for anybody? How is a simple ammeter connected to a circuit? T7DO3 in series with the circuit. Always connect an ammeter in series with it. What instrument is used to measure electric current? An ammeter. Resistance. Use an ohm meter for resistance. That's your question. Question down here. T7DO. 5. Ohm meter. What might damage a multimeter? Measure voltage on a resistance setting. That can destroy a meter very, very fast. Following circuits, measurements your company made using a multimeter. And there's your question down there in your book. Voltage and resistance, a multimeter. Voltage and resistance. What precautions should be taken when you measure circuit resistance with an ohm meter? There's your question down there, T7D1. That's in your book. Make sure that the circuit is not powered. If you're going to measure resistance, make sure you don't have any kind of voltage going into that circuit, because that'll destroy a meter real quick. What precaution have you taken when measuring high voltages with a voltmeter? Voltmeter leads and are regulated so you don't have too small a wiring for it, for use at the voltages to be measured. So you got to think about your wire thickness and the probes that you don't get shocked. Okay, that's module 3A. Now we're going to go on to module 3B. All right. Am I going too fast for everybody getting all this at all? Okay. Ohm's law of power. Let's get back up to this. Ohm's law of power in the metric system. Ohm's law, very simply stated. To measure voltage, you multiply. You cover this up. Voltage is current times resistance. So with Ohm's law, you either multiply or divide. You multiply once or divide twice. So if I want current, current is voltage divided by resistance. Like I say, current, you cover this up, you got the next two. You always divide like this. Now if I want a resistance, it's voltage divided by current. Ohm's law was started back in the early 1800s by a German physicist. At first his theory wasn't accepted, but Ohm's law is recognized worldwide. That's the universal worldwide for it. That's the standard for it. Okay, like I showed you here, E represents voltage. I, which is here, recognize current. R here is resistance in ohms. Like I say, you either divide or you multiply. Multiplying is here, dividing is here. So let's say I want resistance. Voltage divided by current. You want current? Yeah.
Is there a reason why on this one the voltage is represented by E instead of V? Is there a reasoning for that? Or is it just?
That's just the way it's written down. Voltage is V, but on this symbol here, it's represented as E.
Okay, I didn't know there was a reasoning for it.
Yeah.
Stands for electromotive force, which is the definition of voltage.
Yeah. Now, if you look at this down here, it says R equals E divided by I.
SI units.
Yeah. Down here, it says resistance equals voltage divided by current. So you're dividing here. Current, you see here, is voltage divided by resistance. Voltage divided by resistance here. So you always block the one out you want to read, you divide the other two. Voltage, see here, is current times resistance. When you read this way, you multiply. When you do this way, you're dividing. You multiply once, divide twice. And once you block that out, you can read the other two. It's very simple. Okay, just like I showed you here. Current I equals voltage E divided by resistance R. So when you get your pie chart, Ohm's law, you cover up the one you want to read, and you got the other two right in front of you. What formula is used to calculate voltage in a circuit? Voltage E equals current I multiplied by the resistance. So you look in your pie chart, you'll see you can figure it. Ohm's law is not that complicated. Once you get used to it, it's very simple. Calculate resistance in a circuit. Resistance R equals voltage E divided by the current. Like I said before, you either multiply or divide. What is the resistance? Current of 3 amps flows through a resistor connected to 90 volts. Here's your question down here, 30 ohms. What is the resistance in a circuit of 12 volts and the current flows 1.5? That should be about 8 amps. 8 ohms, I'm sorry, 8 ohms. What is the resistance of a circuit that draws 4 amps to a 12-volt source? That's 3 ohms. What is the current flow in a circuit with an applied voltage of 120 volts to resistance of 80 ohms?
Don't give him the answer yet.
I won't.
Hey, you guys figure it out?
Oh. That back, wrong button.
Hold on.
I'm good at button pushing.
You need the current, so you just cover up the current, resistance into voltage.
Yep. .5 amps using Ohm's law. What is the current through a 100 ohm resistor with a connected across 200 volts? 2 amps. So therefore you use Ohm's law again for that. What is the current flowing through a 24 ohm resistor with a across 240 volts? 10 amps. What is the voltage of across a 2 ohm resistor of a current flow through 1/2 amp flows through it? TD1, T5, D10, 1 volt. What is the voltage across a 10 ohm resistor if 1 amp flows through it? 10 volts.
Remember, we needed voltage, so we just cover up the voltage. I times R. It really is that simple.
Yep. What is the voltage across a 10 ohm resistor if 2 amps flows through it? 20 volts. Power, electrons doing work and expended energy. Anytime energy is expended, power is consumed. Electrons moving through resistance expend energy and consume power. Power is the rate at which energy is consumed. Power is measured in units of watts. So he's going to put up another one here for you. Another pie chart. Power equation. Power is calculated as a product of voltage and current, which he's setting up here. Here's power. Okay. Current times resistance. Right here. Power is current times resistance. I'm sorry, current times voltage. Here's your formula right here. E times I. Current times voltage. Voltage is power divided by current. So if you put your marker over here, you're dividing here. Current is power times resistance. Divided by resistance, I'm sorry, it's power, you're dividing here. Like Ohm's law, if you know the two values, you can calculate the third just by covering up the one that you're trying to figure out. This one, this one, this one here. Okay. Electrical power is measured in what units? Watts. What term describes the rate at which energy is consumed? TA or T5A10. That's going to be a question in your book. That's what you look at in your book there. Power. It's all power. What is the formula used to calculate electrical power in a DC circuit? There's your question again. T5CO8. Power P equals voltage E multiplied by current I. So if you look at that chart over here, it looks like Ohm's law, except this, you divide or multiply like you do in Ohm's law there. How much power is used in a circuit when the applied voltage is 13.8 volts DC and the current is 10 amps? 138 watts. How much power is being used in a circuit when the applied voltage is 12 volts DC and the current is 2.5 amps? $30 watts. How many amps are flowing in a circuit when the applied voltage is 12 volts DC and the load is 120 watts? Here's your question in the book, T5C11. Once again, I highlight this. "10 amps. Metric prefixes. This one a little hard to see here. Giga, mega, kilo, hecto, decta. I don't think you do.
This should be in your book as well. If you flip that open, also I'll post the link in the chat to those.
This one here shows electrical units and their namesakes, like ampere. André Marie Ampere, 1775 to 1836. A coulomb is a charge. Charles Augustin Coulomb. Your farad, capacitance, Michael Faraday. The Henry, which is inductance, Joseph Henry. Hertz, Heinrich Hertz, German. Ohms, George Georg Simon Ohm. That's the one I told you about. He's the one that created Ohm's law. Watts, James Watt. Volt, Alexandria Giuseppe Antonio Volta. That's an Irish guy. How many milliamps is 1.5 amps? 1,500 milliamps. What is another way to specify a radio signal of its frequency is 1,500,000 hertz? 1,500 kilohertz. How many volts are equal to 1 kilovolt? That's 1,000 volts. Kilo means 1,000. How many volts are equal to 1 microvolt? One millionth of a volt, which is very, 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 very small. If an ammeter calibrated in amperes is used to measure a 3,000 milliamp current, what reading should it show? 3 amps. If a frequency calibrated in megahertz shows a reading of 3.525 megahertz, what would it show if it's calibrated in kilohertz? There's your question down here, T5B07, 3,525 kilohertz, K is kilo.
Could interrupt just a second.
Yeah, go ahead.
A hint for the test. Most of these type of questions, if you change the period to a comma, that's the answer. Or change the comma to a period, that's the answer. Like if this one here, 3.5, 3,500. So on the test, if you're really stumped, rule of thumb is change the period to the comma or the comma to the period.
I'll put this back up here so you can see it.
That's not going to be every time, but
No.
rule of thumb.
Yeah. You just got to get used to the formulas. Once you get it down, it's very, very simple, just like Ohm's law. Once you master Ohm's law, you can do it in your sleep. How many microfarads are 1 million picofarads? That's your T5B08. That's going to be in your book there. 1 microfarad. What if a frequency display shows a reading of 2,450 megahertz? What is that in gigahertz? Giga means billion. 2.425 gigahertz. Okay. (3B). That's the end of this.
So we're going to take a quick intermission, aren't we?
Yeah.
Short break.
Lock away your last. I don't need it. Throw away your love. It's unrequited. You don't deceive me. I see very small screen. Throw away your love. Oh, you came and tucked your way into my heart. Oh, you look at me in ways I never loved. With you I know that this is all, so I don't need to take it slow. If you want me, then I believe that there's a simple remedy. We don't need no miracle. I think we've seen it all. Just make the call. I'll come running over. We don't need no miracle. It's unconditional. Just make the call, and I'll be yours. I'll come running over. We don't need no miracle. It's unconditional. Just make the call, and I'll be yours. Don't need a miracle. Need a Oh, you open up a world behind the stars. Oh, you make me see the things I never saw. With you I know that this is all, so we don't need to take it slow. If you want me, then I believe that there's a simple remedy. We don't need no miracle. I think we've seen it all. Just make the call. I'll come running over. We don't need no miracle. It's unconditional. Just make the call, and I'll be yours. I'll come running over. We don't need no miracle. It's unconditional. Just make the call, and I'll be yours. We don't need a miracle.
Those medical pills all push me over. I give my fill 3 times a day. These ethanol fumes won't make me sober. One flame to take the pain away. I call you like
Okay, ready to go for the second half of the third one. Last week, you know, I talked about if an atom was the size of the Earth, the electron would be the size of a basketball going around the Earth, you know, a couple feet off. That little basketball, the way we control that thing is with circuit components. The components actually affect these electrons, and that's how we make our radio signals. To make any electronic device, you gotta, like a receiver, we gotta be able to control these electrons. That's what we're going to be looking at tonight of how we do it. Bunch of different components. There is a board going around here somewhere with a bunch of electronic parts on it. You'll be seeing that. These are just a small gathering of electronic parts, you'll see. But we use these parts to control that little bitty electron. Schematic diagrams. We have to know how everything is hooked up. Here's a couple schematics you can pass around to everybody. This is a schematic And code B if you want to get it going back there. That's from a Heathkit HW101. The Heathkit HW101 is an HF transceiver. It is like the 57 Chevy. It's about what the Heathkit 101 is, Hot Water 101. But you can see all the different components that are on that thing. The different colors are the signal paths going through that schematic. So if a technician is working on a radio, he can follow that path and discover where the signal ends up stopping or shouldn't be. We use all sorts of different symbols for each schematic part. This thing right here is a schematic diagram. Can you guys read this okay? It seems kind of dim to me. Could we shut off that one light that these?
That'd be the desk light.
Yeah, the desk light. Way back against the wall somewhere there.
Be in that gang towards the left.
Yeah, now, hope you can see it better now. Basically what this thing could be would be an amplifier. You could have a microphone right here hooked into this thing, and out here you might have a set of headphones. You're amplifying your voice, right? The schematic diagram will show the repairman exactly where the current should be going through. For instance, he'll come in here, and this thing here, the NPN, the current, there's one current going like this in this thing. Then there's another stronger current that goes like this through the output, the headphones. And it keeps going like this. Well, this little bitty current that's going right through here, it's a very small current. It controls how much large current goes this way. So if you've got a microphone, fairly weak output, right, but it will make the voltage on this thing vary, and it will let more or less current through. It's kind of like the water valve on a water line. You can control how much water is going through it by turning it up and down. That's kind of what you're doing with this thing right here. The other thing we'll get into it in a little bit, but if you notice there's some resistors here, R1, R2, and R3. The R1 and R2 and R3 on a schematic, over here on the side somewhere, they'll have R1 listed, R2 listed, R3 listed, and then it will have the value of it, because you need to know the value in case it gets burnt. This might be a 47K resistor. This could be a 1 meg resistor. This could be a 100 ohm resistor. But that's why they have the little 1s, 2s, and 3s on it, so they can be identified to the repairman so he knows what to replace that resistor with. They do the same thing with capacitors and batteries. Here's something neat I bet you've never thought about. Most of you guys are familiar with car batteries, right? You probably changed them and everything. Like I said, the current comes out of here, the negative side of the battery, and then it goes up this way through the thing loading here and back to the positive thing. In your car, when you have the light on, the radio on, the current leaves the battery from the negative side of the battery, goes down into the chassis, and then it spreads out all over the vehicle. Your radio then picks it up from the chassis, runs it through the transistors and everything, out through the on-off switch, through the fuse, and then back to the positive pole of the battery. A lot of people think that current comes out of the positive pole of the battery and goes through the equipment. Just the opposite. It actually comes out of the negative side of the battery, goes through the chassis, up through the equipment, then back out through the on-off, and then through the fuse block. Just something you should be aware of. A lot of the amateur transmitting transceivers will have two fuses, one on the hot line, the positive line, and one on the negative line. That's just to give you an idea. They want to make sure that if something goes wrong, that you immediately stop it here at the source at the minus part of the battery. The resistor. Its idea is to control the function. It's like the valve. You turn up the resistance, less water. You turn it down, there'll be more water going through there. Ohm's law. Excuse me, you had a question you might ask.
Okay, I got a quick question.
Sure.
Going back to the automotive concept there.
Yeah.
Originally, almost all of your old tractors and vehicles were positive ground.
Right.
Now, they changed to negative ground. Does that have to do with the way the electron loss is in the metal? Corrosion?
No. For a long time, they couldn't prove if the electrons is coming out of the negative going to positive or positive going to the negative. It was more or less assumed that it was going out to positive when electronic theory was better known and everything, they realized then that it was coming out of the negative part of the battery. And so then they just started making all batteries or all vehicles negative ground.
No, I agree. Is there actually any difference in electron loss?
No, there should not be any. They always say, you know, if something's wrong in your car, it's always a bad ground. It's because there's a bad electrical connection that electrons have come out of the negative pole of the battery and they go into a corroded mounting bracket or something like that, so they can't get up there. But yeah, it surprises a lot of people when they all of a sudden realize that the batteries work just about backwards is what they thought they do. But yeah, it always comes out of the negative. Batteries, by the let's go back. Batteries, by the way, the long part here, that's positive, and the little short one is negative. So that's common on all of them. The resistor, like we said, it controls that flow of current. When the current goes up, the voltage goes down. We know that because of Ohm's law. This is important to know when you're controlling circuits, voltages on tubes or voltages on transistors. You might use a larger or smaller transistor to make a larger voltage drop or a smaller voltage drop, depending on what it takes to make that tube or transistor work right. This is the older style of resistor. It's a carbon base. You'll see those on that, who's got the list? Or the parts. Oh, start passing that around, please, so they can see them. These are the original type of transistors, the old carbon transistors. New ones are metal film. They're a lot more accurate. These are color codes. This first one is brown. That represents the number 1. The second one, I really can't tell if that's a blue or a violet. We'll say it's a 5. And the orange here is the number of zeros, 3 zeros. So if it's 1, 5, and 3 zeros, means 15,000 ohms.
Was the 5 purple or was the 5 blue? Green, actually.
Green, yeah. It's bad. Okay, the color code. You should have a paper with the color code. There's various ways you can remember the color code. The one I was taught was in the Navy. It's kind of questionable, but it's basically bad boys, black, brown, rape our young girls, but Violet gives willingly. The first letter of each one of those designates a color.
And now you're going to get my YouTube channel.
Yeah.
Some now designates the tolerance.
Yeah.
Tell you what, Russ, I'm gonna pull up a website real quick on here.
Sure.
That'll maybe go over just a little bit better. So let me get that pulled up here.
While you're doing that, the resistor here, you saw that on all the schematics. That's the regular standard resistor. This is a variable resistor. It's got this little wiper on it. It's like the volume control. You turn that wiper where it goes up or down on this resistor, and it allows more or less signal into the next circuitry. It is called a potentiometer. We also call it a pot. You don't want to run a lot of current through this thing, because if you run too much current through it, you'll smoke pot. Yeah, I'm sorry. Ba-dum-bum.
All right, let's see if we can get that website a little up.
Okay.
This is one by Digikey. They sell a lot of electronic components. But
The newer resistors will actually have 4 bands. They get really accurate. The older resistors, like that old carbon one, we're using those back in tube type equipment. A lot of leeway in tolerance on their actual, but with the new stuff, with the new transistors, ICs and everything like that, where it's really close tolerance, you'll actually have 4 colors. The first digit, the second digit, the third digit, and then the number of zeros behind it.
all right, well, this is a little bit interactive here, so it looks like we can select our first band. So Russ, pick a color.
Oh, let's do brown.
Do brown. All right, and then we got our next color here.
Red.
Red. All right, and what's our multiplier?
Oh, orange.
Orange. All right. And then tolerance?
2%. Red.
All right. There we go.
So if you have a resistor and you're looking at it, and the first band is brown, which is the number 1. The second one is red, which means 2. The third one is orange, which means 3 zeros. And then the last one is the tolerance of it, give or take 2%.
And we can see here we got a 12 kilo ohm resistor with 2% tolerance.
2%, yeah.
Yeah, this
universal like across
Yes.
the world?
Yes. Yes, it is.
Do you want to do another one just for the heck of it?
Sure, why not?
All right. So
Let's do yellow,
that's 4.
blue, red,
So same.
and another 2% tolerance, yeah.
There we go. Yep, there you go. Now we have our yellow, blue, red resistor. So we have 4, 6 times 1,000. So that is a 4.6 kilo ohm resistor. No, it's not super clean. Not
Yeah.
super clear on this one.
Yeah, but it's pretty good. But that gives you an idea what those color codes are for, to let you know what the transistor actual value is when you're just looking at it. If you had the schematic, it would be written on the schematic.
You'll share that website on YouTube?
Yep, I'll send a link to that. So.
A capacitor. Remember, capacitor and electrical energy. A capacitor with electrical energy. We'll be learning in just a little bit that a coil or an inductor is magnetic energy. So it's electrical energy and magnetic energy. The capacitor stores electrical energy. It is literally 2 plates put together like this. How big the capacitor is, it depends on how close together they are, how big these plates are, how much voltage is applied. That all affects the actual capacitance of this capacitor, and it stores electrical energy. It can store electrical energy for a long time. Rule of thumb is, if you're going to electronics school, undoubtedly someone will charge up a capacitor, and while you're sitting there half asleep, he'll go, "Here, catch," and you grab it and you get zapped. Yeah, happens every time. That's a capacitor, and like I said, it will store the energy for a long time. It kind of acts like a battery, and it does store that energy with the electric field. The inductor. An inductor stores magnetic energy. An inductor is basically just a coil of wire. This coil of wire can be just literally a coil of wire with air in between it. It also can have a ferrite core in it, an iron ferrite core in it, which helps it transfer energy back and forth. The magnetic energy that's stored in a coil is only there when there's current going through that coil. When you turn off the electrons, you open it up, that magnetic field collapses. And believe it or not, when that magnetic field collapses, we use that collapse to get a frequency going. It stores it, like I said, it's called inductance. It looks like this, a coil with an arrow through it. There again, it means it's variable. We'll learn in just a, yes?
What's the difference between the coil wrapped around air, where this is an inductor, versus a coil wrapped around air, which is a resistor?
Okay, a coil wrapped around air, good for choking off RF current, that kind of stuff. If it's got a coil on it, it will really choke it off. It can also transfer it. Sometimes these Sometimes these things are dual. There's 2 coils around where it's transferring power from one coil to the other coil.
Like an ignition coil.
Yeah.
Primary and a
Exactly,
secondary.
exactly. Yep. The transformer. A transformer is 2 inductors, and they are literally wired right close together. This thing in between them, those are little iron sheets. They prevent eddy currents. You won't need to know that until you go after your general class. But basically what this does, the input voltage right here gets transferred over to this side. Now this could be a step up or a step down transformer. They share that magnetic field. To give you an idea how this thing can be used is out on the power lines. You got that transformer out there that feeds your house, right? It feeds your house, we'll say 110 volts, right? Feeds 220, maybe 440, but we'll say 110 volts. It's taking that 13,800 volts off the power line and stepping it down to the 110 volts coming into your house. So this would be the power line right here coming in, stepping it down to 110 volts. Here's what's really cool. These transformers work both directions. If you would take one of those power transformers off the pole out there, and you hook up 110 volts to it, on the output, there would be 13,800 volts on the output. Yeah, there's a guy that goes around and teaches first responders about electrical safety with power lines. And that's what he's done. He's taken one down, he plugs it into a regular wall socket, and then he's got this 13,800 volts that he can draw arcs on, and it really opens up the eyes of first responders when they have to work around the electrical lines and stuff. The current changes the ratio of voltage and current. If it brings the voltage up, the output current will go down because of the pie chart. It's mathematical. If one goes up, the voltage goes up, the other one comes down. And that's what they're referring to. Electrical units. Each component, each resistor, capacitor, coil, is measured in specific units. A resistor is measured in ohms. You'll have like a 50 ohm resistor. Capacitors are in farads. You might have a 5 microfarad capacitor you're dealing with. An inductor is henries. There again, you might have a 3 millihenry. Milli is 1,000ths. Micro is 1/1,000,000th of a. The designators. I talked a little bit about this on that earlier slide where I said R1, R2, R3. Well, this particular one, it goes all the way up to R10. One little circuit has got like 10 resistors in it. So you can go back and find out exactly what it's supposed to be when you're building it or repairing it. Resistors, capacitors, and inductors. They're abbreviated R, C, and L. Indicators and displays. An indicator basically is just a light bulb that tells you a circuit is on or off. On, off, you turn it on, the little red light comes on. That's all an indicator is. A display, though, if you're talking about indicators and display, a display will actually tell you something. You'll have digital read outputs, something like this. That's the difference between the two. Reactance. Capacitors and inductors, they store the energy, right? A resistor doesn't store energy, it dissipates it. It gets it off in the form of heat. A resistor in a circuit, you put your finger on it, it may be warm, it might be hot. But a coil and a capacitor, they store that in, a capacitor will store the electrical energy, and the inductor will store the magnetic energy. It's called reactance. Instead of just storing it, they call it like reactance to give you an idea. And it opposes the flow of AC current. Doesn't bother with DC, just AC. And remember, RF, radio frequencies, is an AC current. So that's why you'll be looking with reactance when it comes to RF signals. The capacitors have capacitive reactance, and the coil inductor will have inductive reactance. And what we're getting to, they complement each other. It's like a seesaw. If the inductive reactance and capacitive reactance is equal to a particular frequency, the frequency will go zipping right through there with no problem. This is how we make filters. And impedance. It's a combination of resistance and reactance. Remember, the resistance is the flow of DC current, and reactance is a AC current, or RF. The impedance represents an opposition to both AC and DC current. Impedance. So when you hear somebody say it's a 50 ohm impedance line, it means that to an AC, if you could put up an AC ohm meter to it, so to speak, it would read 50 ohms. Resonance. The component's reactance depends on the frequency. When the frequency goes up, the other one will go down, or vice versa. When the frequency goes up, the other one could go down. It's a balancing term with the frequencies. This is important when you're starting making filters, which we'll talk about in just a little bit. When they're equal, when the X sub C, the inductive reactance, is equal to the capacitive reactance, X sub C, X sub L and X sub C are equal, their effects cancel, and this is called a resonant frequency is when they're equal. That means at whatever frequency that you're measuring this thing on, it's very easy to manipulate that frequency. Kind of hard to explain in a short class like this. But anyway, at resonance, when X sub C and X sub L are equal, it only has resistance which applies the AC and DC current equally. You're going to be finding out that, well, here's a good example right here. This is a tuned circuit. There's a capacitor and a coil, and at some particular frequency, X sub C and X sub L will be the same. When it is the same, that frequency can go zipping right through there. If it's not the same, if they're different, then a frequency will have a hard time getting through there. So you can sort of isolate out frequencies you don't want by having the proper size X sub L and X sub C. And like I said, X sub L and X sub C, it does vary with the frequency. Oops. Semiconductors. It's made of a material like silicon. Now, semiconductors, we're talking transistors, IC chips, right? It's made of a material like silicon, and they are okay conductors. They're not as good as like metals like aluminum and copper and gold, but they are okay. They're made out of silicon. Now, here's a thought. You'll ponder about this tonight going home. Transistors are made out of silicone, right? Sand is basically silicone, right? So when you're playing a computer game and the computer beats you, that means that you're dumber than a pile of sand. Yeah, ouch. But that's basically what it gets down to. The impurities added to the semiconductors create the material which has has more than usual electrons or fewer. N-types and P-types. There's two types of transistors, NPNs and PNPs. A diode allows the current only to flow in one direction. The schematic symbol for this thing is this thing right here with the arrow. The current through a diode goes against the arrow. It normally throws this way through there. It has 2 electrons, and I think you do have to know this for the test. They're called anodes and cathodes. The cathode is the negative side, and the anode, of course, is the positive side. It can change AC current into a pulsating DC current. It only allows the current to go one direction. So when you've got an AC voltage here that's going back and forth, you put a diode in there, and now it will just go forward, and it won't go backward. It'll pulse forward and pulse forward. That's the idea, and that's how you turn this one-way direction. You filter it out a little bit, and you get DC out of AC. Diodes are used to change the AC power into DC. They're called basically a rectifier. The rectifier, there's a bunch of different kinds. The little black boxes you plug into the wall that you hook up your phone to charge it. Rectifier. And the transistor. The basic function of a transistor is to control large signals with small signals. There are 2 types, basically, the bipolar and the field effect. You want to get them, they both produce gain. They can also be used as a switch. They can turn the current off and on. Here we go, the transistor. It says here that they can be NPN or PNP. This is how you bias them. You know whether you're supposed to put a negative voltage on one of those 3 leads or a positive voltage. You can't see it very well, but right here there's a little bitty arrow, and it's pointing out. When it points out, it does not point in. So this is an NPN. Just a little ditty to know how you remember which one. The other way, a PNP transistor, the arrow would be pointing in. So it points in proudly. So you watch that little arrow right there, and you can tell whether it's an NPN or a PNP transistor. And like on the other one, the current comes up through here. It goes against the arrow, just like it does on a diode, and it comes through this way, and it makes this loop here. And this loop here is controlling what is going through this way, through the big current. And so that's how they use a little bitty small current to control a great big current this way. A field effect transistor. The field effect transistor came a little bit after the regular transistor. The regular transistor, the PNP we just had or the NPN we just had, you know, it used some current that was going around to control that larger current. Field effect is a little bit different. They just use a voltage here to adjust it. You don't need any current at all. Really neat on a really weak signal because you have just a little bit of voltage. You control the current going through this, going up through the source and out to the drain. And it's controlled by a voltage on the gate, not current. A lot more sensitive. And like I said, the voltage applied to the gate controls the current.
Just a fun fact on transistors, that's what is inside of your phone's central processing unit or your CPU.
Mm-hmm.
Most modern ones have several billion, if not a few trillion in them.
Yeah.
So they're tiny little things.
Oh yeah.
That's where you hear like you'll hear the new phone is coming out on a 7 nanometer process. That is the size of the individual transistors, which
Yeah.
is 7 nanometers.
Very small. The integrated circuit, an IC chip, right? This is basically what ones look like. It's a little black thing that's got a lot of little leads on it. It can have just simple as 4 leads on it. It can have up to 28 or more leads on it. It's a whole bunch of little transistors in one package that's amplifying up a signal or messing with the signal somehow. Protective components. Fuses and circuit breakers. The top thing is a fuse. The fuse here, boy, it's about 50-50 anymore. Sometimes this is the original thing for a fuse. Now they're getting more of a thing that actually looks like a fuse. The glass tube in there with the 2 metal caps on the end. That's the fuses. Once they pop, they're done. You throw them away. The circuit breaker is a little bit different. It will release the connection between the input and the output. So when the circuit breaker goes, just like in a house circuit breaker, you can recycle it, get it going again. Fuses blow, it's a one-time protection. The circuit breakers can be reset and reused.
Is there a way to identify circuit breakers that are self-resetting or anything?
No. A fuse, for instance, will have like 3A on it, which means a 3 amp. A circuit breaker will have like, for a house, it might have 20 on it, or it might have 30 on it.
The smaller ones, though, some of them are like self-resetting.
Yeah.
Trips. Is that marked on them? Or?
Yeah, it will be marked. Yeah. And it's up to the manufacturer, too, on that deal. So you have to sort of know them to know what you actually got.
Some of those will have a tendency to look like this capacitor, some of them look like
Yeah.
Mm-hmm. There's different configurations for them, but it'll tell you on the schematic if it's a one-time or if it's a
Multiple use. Yeah.
There's a term for it that they use.
Yeah.
Manufacturing, I can't think of what it is now.
Bunches of different manufacturers make those fuses, and so they're all a little bit different. Switches. A couple questions on the test about this. Switches are known as single pole, single throw, single pole, double throw, double pole, double throw. A pole means there's just one circuit going through that switch, whereas a double pole has 2 circuits going through it, one through the top and one through the bottom. The throw part means how many outputs it's got. This is a single pole, one current flow going up through it, but it is a double throw that will go out through this little dot or it'll come out through this one. So single pole, single throw, single pole, double throw, double pole, double throw, and then you've got the push button ones, where it is literally you just push in a button, a little metal plate comes down and makes the contact. About that easy. Each position is called a throw. A relay. A relay is like the starter solenoid in your car, right? You hit the starter button in your car, so to speak, you'll throw the solenoid in gear, and that solenoid will bring down the big contacts that actually put all the juice to your starter. It's activated by a current in a coil. The relays are usually single pole, but there's a lot of them that can have 2 throws. You'll go this way or this way. But they can have a bunch of different poles. They might have 4 or 5 different contacts that come together like that. This particular one would be a 4-pole
single throw. Yeah. Other schematic symbols, I think this is in your book. You can't see it very well up here. But these are all just the various different types of transistors, diodes, resistors that you'll come across in a schematic. Questions. What is the ability to store energy in an electric field? The electric field is a capacitor. It's called capacitance. How much capacitance it has. Store energy in an electric field. The basic unit of capacitance, by the way, we're at T5C02. So if you go to the T5Cs, that's the area of the questions we're in at the back of the book. This is the second one in the T5C series. What is the basic unit of capacitance? It's the farad, named after Michael Farad. Basically, how much capacitance, how much energy it can store. The ability to store energy in a magnetic field. The magnetic field is inductance. Electric is capacitance, magnetic is inductance. The basic unit of inductance is the Henry. And it's like millihenries and stuff like that. It's not just a Henry. That's a pretty big coil if it's just a Henry. What is impedance? In T5C12, it's the measure of opposition to an AC current flow in a circuit. A very good prime example of this will be, I think it's next week when we bring in the tape measure 2-meter antenna. A tape measure 2-meter antenna is a directional antenna that you make from an old tape measure. And what really catches everybody off guard on this thing, when you hook up the coax to it, you've got the center coax, the hot, and you got the outer, the shield. You make the two connections, but you'll have a little loop of wire going from the ground to the hot side. And everyone looks at that and says, well, that's shorted out. It's shorted out to DC, but not to AC, not to RF. In fact, it's used as a little tuning stub, but that it always catches people off guard because they look at that little wire going between the center conductor and the shield, and well, that's a dead short. If you have a regular ohm meter, yeah, it'll read a short. But if you could read the impedance of it, it wouldn't be at a particular frequency. The unit of impedance is the ohm, just like resistance. Resistance is ohms, impedance is ohms. What electrical component opposes the flow of current in a DC circuitry? It's a resistor. That's in DC. It will oppose the flow of current. It will oppose it somewhat in an RF current, but there's a few different rules that you don't have to worry about now. But for the test, if it asks this question, what opposes the flow of current in a DC circuit, it's the resistor. The adjustable volume control is the potentiometer. Rule of thumb, if it's a volume control, you call it a potentiometer or a pot. You know, if it's inside on the circuit board, it's sometimes a screwdriver adjustment, and usually those you call pots. But on the outside, you call them a potentiometer, and that's just a rule of thumb. There's no rules saying you have to say it like that, but you can call it either one, a potentiometer or a pot. What parameter is controlled by the potentiometer? It's the resistance. When you turn that wiper arm up, there's more. If you put a resistance here, an ohm meter here, and on this wiper, if it's down here, there'll be zero resistance. But as you turn the volume control up, there's more resistance. And that adjusts the amount of input signal to the next amplifier. What electrical component stores in an electric field? We're getting back to the electric field again. It's a capacitor. So all you got to remember to get these questions right is electric and capacitor, because they do have several questions that they change the question for the answer and the answer for the question. They're basically the same thing. But just remember, capacitor is the electrical field. Inductor is the magnetic field. What type of component consists of two or more conductive surfaces separated by the insulator? And that is a capacitor. On that board around you, there's a big air capacitor. When it comes in and out like this, It's just insulated as air. When they get farther apart, the capacitance goes way down. As it gets together, or as the plates get bigger, there's more capacitance. Magnetic field, inductor. What electrical component is usually just a coil of wire? There again, it's the inductor again. Little coil of wire. It stores it in a magnetic field. When you pull a current away from it, that magnetic field around that little bitty coil starts to collapse. When that magnetic field collapses, it crosses through that coil of wire and puts a little current in that coil of wire. And that's how, if you get the capacitance and inductance just right, you can actually get a transistor to start oscillating, to start squealing. In a public address system, you've heard, they'll come up to the mic and they'll get that really bad squeal feedback. Well, okay, that's an oscillator, except you're doing it on RF frequencies instead of the audio frequencies. What components you use to connect or disconnect? This is a well duh. If any of you guys get this wrong, I'm going to hit you on the back of the head. That's basically what they're asking here. It's just a disconnect, a switch. What component is used to protect other components? The fuse. And there will be a question following.
While
Yeah.
we're on fuses here, Jeff asked in the chat to ask you about the guy who kept returning the fuses because they kept blowing because he thought the fuses were bad.
Yeah. There for about 30 years here in town, I ran a CB shop, electrical sales and service of CB radios. Fuses come into, you can buy them singularly or in packs of 5. Well, this guy came in and bought a fuse off of me, came back in maybe a half hour later and was complaining that the fuse blew, so he bought another one. He bought about 3 fuses, and finally I said, something's going on here, and I asked him about it, and he said, well, yeah, every time he puts his fuse in, it blew, so it was a defective fuse. And I said, no, it's not a defective fuse. You've got something wrong in your radio, guy. But yeah, he was actually thinking I was selling him defective fuses because they kept blowing every time he put them in the radio. There was also a time in, it must have been the mid-'80s, where truck drivers, bless their heart, started coming into the shop and they was wanting to buy 20-amp fuses. Their CBs normally have a 2-amp fuse. They wanted 20-amp fuses because with the 20-amp fuse, it would put out more power. I said, no. Transistor. It is a component that you control the flow of current. There again, with a regular transistor, you use that little current over here to make it go. In an FET transistor, you use a voltage to let the current get on through there. Component that only goes in one direction, your diode. The diode, you can tell a diode, little black thing, tiny black cylinder will have one stripe around one end. The stripe the end on is the cathode, the minus side of the battery. Which component can be used as either a switch or an amplifier? There again, it's the transistor. If you stop the current flowing over here altogether, no current will flow on the big section, so you can turn it off and on if for any reason. It could be an amplifier where the more current over on this side, the more current will be over here. So a transistor can be used as just a regular on-off switch, or it can be used as an amplifier. More than not, it'll be used for an amplifier. Which of the following components consists of these 3 layers of semiconductor material? The silicon. It's a transistor. Which of the following electronic components can amplify signals? Transistor again. Transistor amplifies these signals. Because you got to realize now that when that magnetic wave cuts across your antenna from the guy from Sweden that's talking to you, that little bit of power coming down through that coax. You know, last week we cut a little AA battery into 1,000,000 thin slices. You take one of those little slices, that much power gets down into your radio, and then these transistors start to amplify that signal bigger and bigger and bigger until it's to enough power that it can actually drive your speaker. It's a stripe, and this is a diode can be just a little glass bead with a black stripe around it. That's for signals, really weak signals. The diodes that are black, that's got the silver or white stripe around it, they handle a little bit more current. They will be doing the stuff like changing the AC into DC pulses. The little glass diodes, they're used with, in radio frequency circuitry, very low wattage, very low current. LED, everyone knows what LED stands for, right? Light emitting diode. It's a little diode that emits light. And you see those things everywhere. Everything's got a little red light on them, and this thing does. That's an LED. FET, that's that field effect transistor. That's that one that just takes a little bit of voltage to let the current start going in the output, to get it running up and down really good. That's the field effect transistor. What are the names of the two electrodes of the diode? T6B09 if you're following along. And the names are the anode and cathode. Anode is positive, the cathode is negative. And the term that describes the device's ability to amplify a signal is simply called the gain. If you put 10 watts into a transistor, excuse me for everybody that's studied electronics, but if you put like 10 watts of power into a transistor and you get 100 watts out, you've got a gain of 10. 10 in with 100 out. It says how much that transistor will amplify it. This standard schematic wiring diagram that uses the standard component signals is called a schematic. And you saw the one passing around here, the Hot Water 101 is a schematic. The schematics are pretty well common anymore. There was a transition phase when some symbols are changed a little bit, but anymore they're all about the same. They want to know what the component number 1 is in T1. This thing right here, resistor. And basically what this resistor is, it's on the mic input here. With the voltage that the mic is putting out, it goes around this way. And when you're talking, it goes faster or slower. It gets up to a certain loudness point. It'll cause this little light to come on because this will start to conduct through this battery. There again, the battery, it comes out of the negative part of the battery, down through the chassis, up through the transistor. This does not point in, so it's an NPN transistor, and it lights up your little light bulb. And it's a resistor. Okay, number 2. Number 2 is the transistor. We're all familiar with that already, so we know. Number 3 is the lamp. If it was a diode, light emitting diode, it would look like the little diode with the arrow with some little lightning bolts coming out of it to indicate that it's an LED. This thing indicates that it's a filament light, like a little number 47 bulb or something like that. And of course, number 4 is the battery. And on batteries again, the long one indicates the positive side of the battery, and the little short one down here is the minus side of the battery. Figure 6. That is this thing right here, and that is a capacitor. What this thing might be your little thing that you plug into the wall socket to charge your phone with. You've got 110 volts coming in through here. There's a little fuse on it. Might be an on-off switch. Usually they're hot wired though. It goes through this transformer and it knocks 110 volts down to about 5 volts on this side. And it's 5 volts AC except for this diode here, which only allows current to go in one direction. So it's going this way, goes against it there. So you got about a pulsing 5 volts. It's not a steady 5 volts yet, it's just pulses. This capacitor helps smooth it out a little bit, so it's more of an easy going 5 volt direct current. This little resistor here is hooked up to a light emitting diode, the little red light that comes on. If you've got your 5 volts up here, which is what you want, drops a little bit through the resistor so it gets enough voltage just to light that LED. That's all that thing there, that's the pilot light. This variable potentiometer is so you can actually vary the output, so you can get it right exactly on 5 volts. Or if you needed more or less, you could adjust it to more or less. This thing is called a Zener diode, and it helps regulate that voltage. It helps keep it at whatever you want it at. It can be like a 5-volt Zener that also helps hold everything at 5 volts. But that's basically what this little circuit could be doing and how it basically works. They want to know what figure 6 is. It's that capacitor. And it's like a filter capacitor. You can use it as like a filter capacitor to help filter out that pulsating DC to make it a little bit more smoother going around. Component 6, component 8. That is the light emitting diode again, the on-off light. And 9 is your variable resistor, your potentiometer. And then we go to 4. Figure 4 is this transformer. And like I said, this one is a step-down transformer because it is stepping down 110 volts down to around 5 volts. Yes, sir?
I got a question. You're talking like, okay, the small amps represent chassis, right?
Yeah.
As opposed to earth ground.
Uh-huh.
So you're doing 110. When you're talking chassis of the device that is going to the box?
A little bit of both, really.
If it's 110, it's not automotive.
Right, yeah. On something on this line, when they say the chassis, in older equipment, it was the actual metal chassis of the case. Now, with circuit boards, it could be isolated. You might have a chassis, a foil that is acting as the ground. It's not actually on the chassis. It's not connected to the chassis.
Basically the return path for the current in the circuit.
Yeah.
It's not a metal case, and it's probably just a stripe on the board.
Yeah.
Circuit board that they use.
I got the circuit or TV circuit board that does that. I may bring that out after a while. Show that.
Yeah.
And your electron flow is actually coming through the chassis back around to the positive side.
Yes. Yes. Going back to it here, this thing here, that means it's got an iron core, little laminated sheets of iron. When you've got this magnetic field cutting across this magnetic field, this 110 volts cutting across here, producing 5 volts, there's little eddy currents come up in this thing, and that eliminates eddy current, eliminates loss. If it was transmitting an RF frequency and the radio frequencies, you would do away with this iron core altogether. Just a difference between the lower cycle, 60 cycle stuff and the RF stuff. Figure 3, a variable coil. What they're doing here is they're tuning their radio up to this antenna. They want to make sure everything is 50 ohms, and by adjusting the variable, by adjusting this variable capacitors and the variable coil, when you get them all set to a certain frequency, only that certain frequency will go up and out the antenna. If they're misadjusted, other frequencies could get up to that antenna. Like we said last week with the fundamental and harmonics, if you got it tuned right, it'll just be the fundamental frequency. The one you want to operate on will be getting up to the antenna. If they're mistuned, then those harmonics, the double frequencies, can get up to the antenna, and then you're messing with other bands, screwing them people up from talking good. The symbols on each one of them indicates an electrical component. Every little component you see in that schematic around there is a component inside the radio somewhere. But they represent each electrical component. It might be a resistor, it might be a coil, it might be a capacitor. Which of the following is accurately represented? It's the way the components are connected. On most schematics, there'll be, when two lines come together, if it's got a large dot in between the two, it means that they're connected, they're soldered together. Sometimes, if they're not, usually it's got a little loop going across it. The line will have a loop, indicating that they're not connected. But it shows the way they're connected so the technician can actually, literally, follow the signal through the radio and find out where it quit at. Devices that changes the alternator current into direct is the rectifiers. And a rectifier is a whole little circuit. It changes the 110 volts down to maybe 12 volts. A relay, and there again, it's an electronically controlled switch. You put some voltage to it and it'll throw the switch automatically for you. You don't have to go in there and literally throw the switch. The little coil will snap it back and forth for you.
I got one of those too. I'll show it. Bring
Okay. They want to know the type of switch this number 3 was. It is a single pole, single throw. Single pole means there's only one path of current going through the switch, and a single throw means it's just one position where that current is going to go to. So it's a single pole, single throw. The type of displays that display a, this is kind of a weird question, or the way it's presented, displays an electrical quantity as a numeric value, and it's a meter. That meter is showing this how much current is going through a wire, and that meter will say 5 up here, or it'll say 7. So that's what they're talking about. The meter is telling you how much current is going through the meter. It's just kind of worded silly. It kind of catches some people off guard. What component is commonly used to change this 120 volt AC down to a lower AC? And that's the transformer, a step-down transformer. And what is commonly used as just a visual indicator? An on-off light, a light-emitting diode. And we see those everywhere anymore, light-emitting diodes. What is combined with an inductor to make a tuned circuit? An inductor and a capacitor. You put them together and you've got a tuned circuit. And we'll learn in just a little bit why we want to put inductors and capacitors together in a tuned circuit. This is a device that you put a whole bunch of transistors into a little teeny tiny case. An integrated circuit, an IC, integrated circuit, IC chip. Back in the day, when I graduated from electronics school, it was back in '67, in the last millennium. When I was getting out of electronics school, they had a new thing come out called an RC, and it was resistors and capacitors in a little group. And we thought that was so amazing. Boy, they're getting things smaller and smaller. And then they made from tubes, they went down to transistors to make stuff even smaller. And when they got to IC chips, they took all these very small transistors and reduced them down to put them inside an IC chip. So the size, and we all know the size, from the original bag phones, cell phones, now down to the little flip phones. Things just keep getting smaller and smaller with these integrated circuitry. Function of number 2. What is number 2? Oh, that's the transistor. The function, and its function is to allow that current to go through that bulb and light up the bulb. It allows the flow, it controls that flow of current. The transistor does. In this case, the flow of current is simply lighting up that light bulb to let you know that the circuit's on, the switch is on or something. But it also can be, a signal or something you're running through there. What is a resonant or tuned circuit? It is that conductor and capacitor, and it's either connected in series or parallel. Now, when you're dealing with a particular frequency, there's a formula to figure out how big your capacitor and how big your inductor has to be, how many farads, how many henries it has to be. If you put them in series or in parallel, it will either let this one frequency go through real easy, or it will block the frequency from going through there. The purpose of the fuse is to interrupt power in the case of an overload. And I got to impress upon you again, if you blow your fuse, right, you can go down in the fuse and it might hold it. You can go up just a little bit. If you got a 5 amp fuse and it blows, maybe go up to a 7 amp fuse, but don't go up to like a 10 amp or 20 amp fuses, because what will happen, the actual wiring inside the radio and even the insulation on the wire going to the radio can actually catch fire and start a fire. So you always, like it says here, why is it unwise to use that 20 amp fuse in place of a 5 amp fuse? Because you can cause a fire. It's very important on that. Okay, number 3. We're ready for 3D. The last end of this thing. In 3D, we're going to be covering various circuits that's in radios. Just a handful, there's not that many. But you need to know a little bit about these circuits and the circuits that use all these components and why we use certain components in certain circuits. We're getting there? All right.
Hold on just a moment. It's not updating on my side.
Okay. No problem. We ready yet?
Not quite.
Uh-oh.
Tool I'm using to screen the screen from this one. First stop working. I'm just going to restart real quick and then hopefully it should be good to go.
Each particular circuit in a radio usually has one function. And that's what we're going to be talking about, a particular circuit and what it does to this radio signal that you guys are playing with.
Not quite ready.
Oh, okay. Well, you got windows on that thing?
May have killed it.
Oh, no. Murphy has struck.
Murphy was an engineer.
There we go. Now, check.
Types of radio circuits. There's only a few types of radio circuits, but we do want to go over them tonight. The basic transceiver. Virtually all radios you're going to buy nowadays are going to be a transceiver. A transceiver has both a transmitter and a receiver in one little package. A CB radio, a CB transceiver, it transmits and receives all in one little box.
Russ, hate to say it, it ain't working quite yet.
Uh-oh.
Give me one moment.
Sure.
We need to get some Jeopardy music, but I'm pretty sure that's copyrighted, so we can't play
Can't do that on there.
It was on there until you went full screen on that.
Okay. Make some adjustments there. I think now I believe we are.
Should we radio now?
Yeah.
Yes or no?
Not quite.
Not quite.
I apologize for this. It's working so good, and now all of a sudden it just decided to quit out on me.
Yeah, blew a fuse. Let's get a big fuse and put in there. Make it work better.
Actually, it's kind of funny, as Apple is known for, on their computers, for using indestructible fuses. So literally everything dies except the fuse in their laptops.
A crowbar that protects itself.
Pretty much.
A couple of minor notes on capacitors and inductors that weren't brought up, but you'll need to know this eventually. Capacitors will not pass DC.
Yeah.
Inductors
Will.
Capacitors will only pass AC. Depending on the value of the capacitor determines what level, what frequency of AC it will pass, or range of frequencies.
And a lot of times if your radio, if your radio goes down, it's a lot of times it's because your capacitor, a little filter capacitor, is shorted out, and it's allowing DC to go through it. You don't want DC to go through it. Easy to find. You just put your hand on the circuit board, and you can find out which capacitor is really hot, and that's the one that's shorted. Yeah, yeah.
What's the difference between a capacitor and a condenser?
Same thing.
The condensers are used in DC
Con-
circuits, though, right?
yeah,
That's
condensers.
the automotive terminology
Yeah.
from way back when, but it's the same.
It's the same identical thing.
I guess you lost me when you said capacitors would only work with AC, but a condenser works the same as a capacitor works with DC?
No, it doesn't. No capacitor or condenser of any stripe will pass DC, period. If it does, it's busted.
Yeah.
That makes
The
a lot of sense.
the condenser that's like in the old set of points, that was not passing DC.
Okay, so it's, the difference is the condenser's storing it, but it doesn't.
It's like it's storing it, yeah,
Okay.
to give it a boost.
All right.
We'll
I
say it
think
like
we're
that.
good. Why don't you go back a slide there? Yep, I think we're good to go.
Good.
So
Okay. The radios that are transceivers, most all of them are transceivers today. The HF rigs that you can talk around the world on, the 2-meter radios are all transceivers. They're a transmitter and a receiver in the same box. Now, have to have a switch on that sucker going up to the antenna. You cannot transmit if you don't have that switch. It would go straight into your receiver and blow up your receiver. So you got to have in a transceiver, you have to have something to switch either the transceiver and receiver on and off, or to get it to go up to the antenna, to get the transmitter to go up the antenna, and then you're releasing the antenna from the receiver. So you don't feed the transmitting signal straight into your receiver. That's abbreviated XEVR for transceiver. The switch is connected between the transmitter and the receiver. It's this area right in here. And that's what switches the antenna. When you're transmitting, it goes up here through the switch. Up, when you're receiving, it comes down over this way, and this is disconnected. You got to disconnect the two. That's in a transceiver. Now, it allows the single antenna to be switched between when you're going from back and forth. It is usually inside the radio itself, the TR switch. It can be a circuitry, not just necessarily a switch, but it's always inside the radio because you can't transmit and receive at the same time like you do on a repeater, because a repeater relays these signals, and we'll go through a whole section about repeaters and how to get into repeaters and use repeaters. But to understand that in a repeater, it is receiving your little weak signal from your walkie-talkie. It's coming down the antenna. It's going into the receiver of the repeater. From the receiver of the repeater, it's fed directly into the transmitter, and then the transmitter transmits it back up to the antenna. It's one big vicious loop like that, where the transmitter and the receiver are working at the same time through the same antenna. The reason one doesn't burn up the other one is because they're on two different frequencies. And that's what keeps it apart. That's what the duplexer does. This thing. The duplexer is basically, if I could describe one physically, you get some little metal cylinders, all different sizes, maybe this tall, maybe this big around. There might be 2, 3 of them together. They'll be all connected with little coaxes, and they're a really sharp-tuned filter. They let the one frequency that the transmitter is transmitting on go up to the antenna and not let it get over to the receiver. And they are at the same time it's transmitting, the signal coming down is going into this duplexer, and it's going over to the receiver, so they don't mess with each other. It's called a duplexer. So every repeater will have a duplexer on it. Some of them are small enough where they can actually go inside a very small box. Some of them are great big ones. Up at the sheriff's department, the duplexers up there are about 5 foot tall, to give you an idea. They're big. The duplexer we've got on our 2-meter repeater up on top of St. Anthony Hospital is only about this tall. So it depends on how much, their physical size depends on how much power is going through them and the frequency. Now, what happens when you're radio? First of all, you start transmitting a signal, right? Then you got to put some sort of information on that carrier. You're modulating it. It can be voice, data, video, it could be a little bit of anything. The information, that voice, is converted into an electrical energy. That electrical energy is then added to that radio, still inside the radio, in the modulator section, and then that radio wave goes up in your coax, out through your antenna, and then out into the world. the guy on the other end of the world, or the other end of the county that's talking to you, your signal is now hitting his antenna, setting up a little bit of current flow in the antenna, coming down the coax, and is going in to the radio. And then that radio takes that really weak signal and it starts amplifying it, amplifying it, amplifying it, until you can actually use that signal to do something. Either run a digital, hook it into the computer, use it for voice, for FM, anything like that. An extracting formula can be very simple and it can be very complex. And they say this is what makes radio fun, learning all about how the radios work, learning how some of these circuitries that I'm going to start talking about actually work and what you can actually do with the radio. It's some of the most amazing things. It is the art and science. Like I said, you know, it was basically amateur radio that invented email way back when. So filters. Okay. Filters act on signals differently according to their frequencies. A filter can reject, enhance, or modify signals. And we are going to go through these type of filters here. I think it's in your book somewhere if you can't see this very well. There's basically 4 types of filters we'll be talking about. The first one is the high pass filter. And then there is the band. Gosh, that is out of focus, isn't it? See if I can get that a little bit better maybe. A little bit better. Anyway, there's a band pass filter, a low pass filter, and then there's a notch filter. The first 2 I'm going to talk about is the band pass filter and the notch filter. This is the radio you're looking at. You're on 15 meters, 21.2 megahertz, and each one of these represents a different radio station talking to them. Now, if you just had a regular radio and tuning it up here, you would hear all of these guys at the same time. It would be a mess. So you use what is considered a band pass filter in your radio. The band pass is inside your radio, and you can adjust it. If you want to listen to this guy in the red, you can adjust this filter, and it's like a window. You can adjust it so it's just him coming into your radio. You can go one side or the other, but you can get that band pass where you can just pick him, and the rest of these signals will be ejected. That's the band pass filter. You will use that a lot in the radios, especially if you're working DX. If you're working DX, it means you're working somebody in a foreign country that everyone's trying to talk to. Peter One Island down by Antarctica. Everyone's trying to talk to him when they have a de-expedition to go down there. And so you use this thing just to get everyone else out of there so you can just hear him. Now, if for some reason you want to talk to this guy right here, this guy in the green. You want to talk to him, and there's some klutz right next to him sending out a dead carrier, really covering up his signal bad. That's when you use the notch filter. And a notch filter is like this. You turn the notch filter on until it covers up the red, and it's letting the green through. The notch filter knocks out or eliminates one particular frequency, or frequencies close to it. So you can knock them out. If you want to listen to this guy, or if you don't want to listen to him, you can get him totally out of your radio. This guy that's throwing the carrier, you can drown him totally out, where you can still hear the guy in the green with no problem. So that's what you, when you're contesting on like field day or sweepstakes, there's a bunch of frequencies, all of them being used, and you try to connect with each one of them, and that's where you can use the notch filter if there's someone really strong. If you're trying to talk to this guy, and this guy here is just covering you up, you use a notch filter to get rid of him. That's where you use the notch filter. Now the high pass filter and a low pass filter. What it is on a high pass filter and a low pass is we used to have a lot of trouble with it, but when they reallocated the television frequencies, we don't have that much trouble anymore. But what it was is a high pass filter and low pass filters, the most common ones were usually centered around 30 megahertz. And what it is a low pass filter would pass anything below 30 down to 3. This is your HF band, right? A high pass filter would pass stuff through the higher bands. And what this does is, if you were transmitting, C-beers were really noted for getting into TVs years back. A C-beer would have way too much linear power. He'd have the modulation turned up way high. He would be splattering, and he would be getting into their neighbor's TV. So what he should done, he should put a low pass, because this is the amateur band. The television frequencies are up here. If he would put a low pass filter on his radio, it would pass all these low frequencies, but it wouldn't pass the high frequencies, and therefore he wouldn't be getting into his friend's TV. The low pass passes them low, the high pass. The guy with the TV that's having trouble with you, he would put a high pass filter on his TV. It would pass the higher frequencies, all the different TV channels, but it wouldn't pass the lower frequencies that was causing the interference.
Or you put a pin to the dude's coax.
That works excellent.
Back in the old TV days, the 6-meter band was a big offender on television because it was right below channel 2.
Yeah.
The guys who were working with 6 meters, especially in town, running what we call a full gallon, 1,500 watts will wipe out the entire channel 2 to channel 3 spectrum.
Yeah. It was usually always channel 2 or channel 3 that was getting wiped out by performance because of the fundamental frequency of the CB band. The TV was twice it. CB was on like 28 megahertz. The TV bands are 56 and up or thereabouts.
6 meters was the biggest offender.
Yeah. But anyway, that's the difference between a high pass filter and a low pass. You guys would, if you're interfering in people's TVs, you'll want to put a low pass filter on your radio. This low pass filter is outside the radio. You will, where coax comes out of your radio, you plug that into the low pass filter. The low pass filter would then go on up to your antenna. The high pass goes on right on the back of the guy's TV. So the signal coming down from his antenna, his TV antenna, will just be passing these high bands, the higher frequencies. That's the difference between a high pass and a low pass. Modulation, that's when we add something to the radio wave. If it can be Morse code, speech, data, anything. Anytime we put some information on an RF carrier, we're modulating it. There's different kinds of modulation techniques. The main two that you guys will be messing with will be the amplitude and frequency. You'll be taking a radio wave and you'll be making amplitude vary, like if you're on voice or something. If you're talking FM, you make the frequency vary this way. AM is like this, frequency, FM is like this. Phase, you don't really need to worry about that at this point. So basically, there's modulator and demodulator circuits. The modulator is in the transmitter, the demodulator is in the radio. Every radio receiver has a demodulator. It might be different types of circuitry, but they will all have a demodulator. The modulators add this information to the RF signal, and the demodulator takes it out. Changing frequencies, a mixer. A mixer is a circuit inside the radio. And what the mixer does, it takes your receiving signal and an oscillator that's inside your radio, and it puts those two, mixes them together, and then the output of the mixer is one frequency. The reason this is good, because if you want to amplify frequency signals, if you just have to amplify one signal, it's a lot easier. You can amplify it a whole lot. So if you got this signal up here you want to listen to, you adjust your oscillator down here so that the equivalent frequency coming out is this one standard frequency you'll have in your radio. If you want to go to a different frequency, you change the frequency of this oscillator. So if one comes down, the oscillator frequency might go up. So when they combine, the output will still be that one constant frequency. 455 kilohertz is a common radio frequency for radio receivers. 455 is common in a lot of them, in fact. But that's the idea of the mixer. It's just like a paint mixer. You pick some white paint and some red paint, you're going to come out with pink. It's going to be a different color. There are some more things to know about the mixer. It's not important. The big thing you need to know about the mixer, though, is that you are combining signal frequencies, and the output will be another frequency. It's called heterodyning. Back in the very early radio days, A radio, you know, was a nice big wooden box, and there's about 4 or 5 dials across where you had to tune in each individual circuitry. Well, they came up with heterodyning, and they found out that, boy, all you needed was one oscillator, and you could cover the entire band. The 2 signals are combined in a mixer. It generates a mixing product. On the output of the mixer, there is the sum and the difference. So you have a frequency up here and a frequency down here. The output will be the sum of these 2 or the difference of these 2. You can take your pick on which one you want to use. They'll both have the same information on them. Shifts frequency by adding or subtracting. In FM circuits, you'll be using that thing. There is a thing called a multiplier, and a multiplier just literally multiplies that frequency. If you were on 21.2, if there's a multiplier in there, in your circuitry, it would boost it up to like 41.4 megahertz. 2 of the things you're going to look at when you buy a receiver: the sensitivity and selectivity. The 2 essential tasks of it. The receiver is supposed to hear this signal, and then you only want to hear the one signal. You don't want to hear, well, all of them that was on this board. You just want to hear the one. That's the selectivity. The sensitivity is how sensitive that receiver is, how weak of a signal it can pick up and amplify it. The selectivity is that measure where you can only pick up one of those frequencies. You can be very selective about which frequency you want to listen to. And there again, the sensitivity, like I said, microvolts, very small. A receiver is another little piece of equipment, a preamplifier. A preamplifier is a separate little box usually that you put in between your receiver and your antenna. All the signals that are coming down that antenna, all the signals, doesn't matter what band, all the radio frequencies coming down that thing come to this little preamplifier, and it starts to separate them out and amplifies the section that you want to hear. Makes your signal, makes that really weak signal a little bit stronger, so you can hear it a little bit better. And it is between the antenna and the receiver. A transverter. A transverter is another piece of equipment, and what it does, it converts a transceiver to operate in a different band. And by that I mean, there it is. You might have an HF radio operating on 28 megahertz on the 10 meter band. You can put it into a transverter and it can come out on 222. That's 1.22 band VHF. So you've got an HF that you can actually get it to transmit on the VHF bands.
People are doing like gigahertz stuff.
Yeah. This one here, you got a 2 meter radio. It operates on 144, and it's converting it up to 10 gigahertz, the really super high frequencies. But that's a transceiver. It changes from one band to another band. That's sort of the secret word you got to remember, from one band to another one. The questions. We're at the T1F09s. What type of amateur station simultaneously transmits the signal of another amateur station on a different channel or channels? It's a repeater station. You've got your little handheld here. It transmits, it goes up to the repeater on top of the hospital, comes down the repeater, into the receiver, out the receiver, into the transmitter, and then back up through the duplexer, back up and transmits out again. The ability to detect the presence of a signal is simply how sensitive it is. You want it really sensitive. What is a transceiver? It's a unit that combines both the transmitter and the receiver into one little radio. That's a transceiver. Which of the following is used to convert a radio signal from one frequency to another? And that's the mixer. That's when we're taking this one frequency up here that we're listening to. You bring it down, you couple that in with an oscillator, and it comes out that mixer at a different frequency, one that you can actually start amplifying really well. The thing that discriminates in a receiver between multiple signals, selectivity. It can be very selective of which signal it gets. The name of the circuit that generates a signal at a specific frequency. That's the oscillator. It oscillates. It makes another frequency. Your car AM radio, or FM radio, you go in your car, you turn on your radio, you can turn the dial, and you can go across the band and pick up a whole bunch of different stations. That's the oscillator. It's a variable frequency oscillator, a VFO. Now, when you find one you like, you put it in your memory. You poke number 1, you find another one, you poke number 2. Handhelds and stations are exactly like that. You've got the VFO function where you can go up and down the band and transmit and receive, or you can go into your memory mode where you can have your favorite frequencies or favorite repeaters programmed in there. This is the thing that converts to another band, like we're going from 2 meters up to the gig. It's a transverter. Probably, and I'm just guesstimating here, probably maybe one of you might use a transverter. There are just not many people use them, but they are there. What describes combining speech with the carrier? Modulation. You're modulating the carrier with speech. You could be modulating it with CW or data or anything, but this one. What device increases the low power output from a handheld transceiver? It's an RF power amplifier. Now, if you're in your car, you can hook your handheld up to your little magnetic antenna on the roof, and you can talk to maybe our repeater in here in town on a 10, 15-mile radius. If you get a power amplifier, you stick it under your seat, you hook it up to your handheld, and that power amplifier could put out maybe 25, 50 watts. So you can go a long way from Effingham and still get back into our repeater. That's the power amplifier. It's a separate unit. And where is a preamp installed? Everyone calls them preamps. They don't call them preamplifiers. You put a preamp in. You put your preamp in between the radio and the antenna receiver. And that's it. We're done. Free at last. Tomorrow, next Thursday night is Module 4. And it's really interesting because we get into propagation, antennas, and that kind of stuff. We have a lot of show and tell for next week. But read Module 4 next week.
Does anyone have any questions before we get going?
Any questions?
All right.
If not, drive careful going home. It's cold out there.
Lock away your lust. I don't need it. Throw away your love. Oh, you came and tucked your way into my heart. Oh, you look at me in ways I never loved. With you I know that this is all, so I don't need to take it slow. If you want me, then I believe that there's a simple remedy. We don't need no miracle, I think we've seen it all, just make the call. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. Don't need a miracle. Need a Oh, you open up a world behind stars. Oh, you make me see the things I never saw. With you I know that this is all, so we don't need to take it slow. If you want me, then I believe that there's a simple remedy. We don't need no miracle, I think we've seen it all, just make the call. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. We don't need no
Those medical pills that push me over. I kill my fill 3 times a day. These ethanol fumes won't make me sober. One flame to take the pain away. I caught you lighting matches in the back room. Haters look mad when they pass you. Let's talk about around when it's past 2. Reach a glass to know. You don't gotta fight alone. You don't gotta fight alone. Don't be so personal. Take me out of the Everyone's seen death in their dreams, but we still wake up and go to sleep. Everyone's seen death in their dreams, but we still wake up from our sleep. I'll be home soon. You don't gotta fight alone. You don't gotta fight alone. You don't gotta fight alone. Don't be so personal. Take me out of the road. I'm going under. Take me out of the road. I'm going under. Who do you rely on now? I know the worst. I know the worst. Who can you call on now? I know the worst. I know the worst.
How many lives does it take to realize what's going on? How many years have gone by? When will I reach the finish line?